Hello, everyone. This is lecture 8 of PTRE 465531. We will talk today. I uploaded the homework 1, last Friday afternoon, and I said it's gonna be due next Monday. So not today, 1 week from today. And the way I could set it up in Blackboard, the latest time I could set it up is 11:59 p.m. So 11:59 at night, 1 minute before midnight. I couldn't do it midnight exactly. So the homework is really due on as soon as 11:58, 59 hundredths of a second. The next second is like basically becomes 59, and then it's late after that. So don't wait until the last minute. Yeah, 11:59. That's what end of the day is for Blackboard, the calendar on Blackboard. Anyway, now if you open it, and you will find it where? If you come to Blackboard and go learning modules, here with purple, I have the homework. You click on it and you can see it. First question is pretty simple. Eigenvalues, eigenvectors, to find the principal stresses and axis directions. Then I have a big question with 40 points. The following table contains the estimated bulk mass densities for an offshore location as a function of true vertical depth below the sea, the subsea, well, in the subsea, below the sea, I should say. Water depth is 500 meters. Measurements indicate that porosity of layers estimated through electrical resistivity readings. And we will talk about that today and Wednesday. You are asked to plot the profiles for SV versus depth in MPa and PSI. So MPa against meters and PSI against feet. Plot the profile of a hypothetical hydrostatic pressure for brine, both axes, and assuming that the brine density is 1,031 kilograms per cubic meter. Additional compaction lab measurements on shale cores indicate a good fitting of the porosity effective vertical mass stress relation of this. We are going to talk about this today. This equation. Phi is the porosity. Phi sub O is the initial porosity. And the beta is a parameter. We're going to talk about that. Estimate the actual pore pressure in shale. So basically, you need to solve this equation and somehow calculate the pore pressure from it as the depths go down. According to porosity measurements, does the vertical effective stress always increase with depth? Please justify. You are encouraged to summarize all lines in unified plots, one per unit system as a function of depth, inverted vertical axis, basically a pressure traverse plots that we are looking for. Show your data, and this is the data. You have depth, you have bulk mass density, and you have shale porosity. Now, from depth equals 0 is the top of the sea, is the sea level. And then you go down, you see I have here shale porosity not applicable, because you have water. There is no shale porosity in the water. And then at, what is it that you hit the first sand? At 6,000 feet, you hit the sand, water becomes sand. And then you still do not have shale porosity because sand is not shale. Okay, and then we go deeper. We're going to talk about it in class and probably it's going to make things clearer. You hit shale at 1,200, and there you have porosity. So you have porosity data after 1200. Notice how the density of the water changes as you go. Huh?
We noticed that.
Yeah. So this is how you need to input that into your approximation to get SV. Now, question number 3, not that terrible. The following image shows a stress log for an offshore location. What would you say is the approximate range of the depth shown on the stress log? What is the approximate depth at the location of the unconventional reservoir? Answer specifically at the location of the dashed line. Same for the following questions. What is the effective minimum and maximum horizontal stresses? A keyword here is effective. So I'm looking for sigma, not S. And is the reservoir pressure hydrostatic? And what is the effective vertical stress? Now, effective again, vertical stress. And what is the stress regime? Stress regime, I'm looking for a word, not a number. Normal, strike, slip, reverse. Okay, let's see the logs. Okay, they come from an SP paper, and it does not have scale on the axis. Okay, it doesn't have scale on the vertical axis. It has a scale for the Y, what you are looking at. I give you the pore pressure, but it doesn't give you any vertical axis. Now remember, we said about the rule of thumb, about the overburden. Yeah, 1 psi per foot.
When you solve for it.
And I told you you can apply it if you are not given any other information. So you can get that from here, count some boxes, and figure out the depth range. You see? And then the rest goes from there.
It's basically the reverse from the exercise too.
Yeah. Well, I will say, as a friendly advice, do question 1 first, then question 3, and then question 2. Based on the things that we do in class, the way that we go in class. Because we are gonna be doing stuff that will be helpful for question 2, probably through next lecture as well. But yeah, those are the questions. 1 second. I am sharing and I am recording. Okay. Okay, for question number 1, I think it's pretty clear. Principal stresses, you do the eigenvalues. Principal directions, you do the eigenvectors. Fairly straightforward. Comment on the stability of each stress state, I think it's pretty straightforward. Then let's go to question number 3. Then we say, what did we say in class about the stability of a stress state? When it's depicted, when it's written down as a matrix. Then we say that the matrix has to satisfy some sort of criteria.
Normal stress.
No, stability. You can have shear stresses.
Yeah, we said we have diagonals, right?
Yeah.
No, it means it's not stable.
Yeah. So do you expect to see those stresses in real life? Yes or no, and discuss basically. The following image shows a stress log on location. So what would you say is the approximate range of depth? I think I pretty much answered it. We said about the rule of thumb of 1 psi per foot. What is the approximate depth at the location of the unconventional reservoir? Okay, if you found the range, I think it's very easy to come here and say, excuse me. By now, because you did part A, you know the range. I will take a green color. This is my unconventional. Tell me what is the depth here. And you find that. So now you knocked out part B too. Excellent. What are the effective minimum and maximum horizontal stresses at that point? Keyword here is effective.
Yes.
Do the logs show effective or
Yeah.
no? So you need to convert them to effective. Okay, so easy question.
Convert from S to sigma. Then.
Yeah. You need to give sigma. You are given S. Is the reservoir pressure hydrostatic? And what is the effective vertical stress? I mean, you know the pore pressure, but now you also know the depth. The pore pressure is 42 MPa, but you know the depth. You can convert it and see if it's hydrostatic. By the way, this is an onshore reservoir, no seawater above you. So, what is the effective vertical stress? Very easy, sigma V. And well, what is the stress regime? Yeah, very easy homework question. Now that you have done everything, we come to question 2. And we have to take this data and make a nice spreadsheet. Yeah, or you can do it on MATLAB or Python, whatever you want, as long as you get the right answer. Plot SV versus depth. You do it for MPa and you do it in versus meters. There you have to use G. And then you do it in feet versus PSI. Same thing. Why did I say MPa versus meters? And then here I should have said PSI versus feet. I want PSI on the y on the x-axis and feet on the x-axis.
The y-axis.
Yeah. Oh yeah. Sorry. Pressure traverse, feet on the y-axis. Pressure, stress on the y. Additional compaction lab measurements. Okay, so we are gonna see that in class. This equation. This equation is a little bit like the hydrostatic value that I told you. You only use it if I tell you so. Same thing for this equation. It's good for shales under given conditions. It's not good for everything. So it's a nice approximation if you are dealing with mud rocks at given conditions, but it's not good for everything, like universally applicable. So be careful where you use it. Now, obviously, I told you, you can use it for the shale in this location here, like from 1200 to something else. Let me get the pen. It's applicable from here all the way down.
The shape.
Exactly. Only here is applicable. Phi equals phi sub O E.
Minus, no, beta.
Minus beta. Yes.
Minus beta. Yes.
And then sigma V.
Sigma V, yes.
Okay. Also notice something. Sigma V, not
Yeah.
SV.
It's the compaction index.
Yeah.
Yeah, this equation.
Yeah.
It's the
Yeah, I didn't want to give the name, but yeah. It's good for mud rocks at pretty wide range of conditions, but we cannot be using it blindly. So if you know porosity, it doesn't mean that you can find everything else using that equation.
It's kind of empirical.
Basically, we need
Yeah.
to find the sigma.
Exactly.
To apply this equation.
Yeah. And remember, the equation have sigma V.
That's the
Okay.
thing, you need to find
Yeah.
sigma V to apply.
Sigma V includes pore pressure. Okay, so now you have a relationship between porosity and pore pressure.
Yeah.
Right? Yeah. Beautiful. I hope that is that clear in the mind of every student. They are gonna do this homework. Okay, pore pressure. Okay. What depth is there overpressure? If so, what depth does it start? Overpressure is when the pressure goes above hydrostatic, exceeds hydrostatic
It's the pore pressure.
of the hydrostatic of fresh water.
Yeah.
That's when you get overpressure. And I think if I ask this question, there should be overpressure somewhere. According to porosity measurements, does the effective stress always increase with depth? please justify. I mean, that's a judgment call, not a judgment call.
You didn't give the pore pressure in here.
No,
Oh,
but I gave you an equation that has
Yeah.
pore pressure.
yeah,
It's just not seen the way it is.
yeah.
Remember, we're gonna see it today if we have the time, but just to tell you that from this equation and what you know right now, you can rewrite this equation to phi equals phi sub O E minus vita sigma V minus PP. And here is the pore pressure, right? So you have a relationship of phi and pore pressure. Phi and pore pressure. Now, if you come you have phi, sorry, trying to write on top of the screen, it doesn't let me. This one, you have phi.
Yes.
So you can very easily use that equation to get the pore pressure, rearrange it accordingly, etc.,
Yeah,
etc.
Yeah.
Okay, this is about the very easy homework number one. Yeah, yeah, yeah. Yeah, you just move it mathematically, manipulate it as you like. Any questions on homework one? Any questions from the online people? No. Okay. Let's proceed. Okay. I need to move this here. Last time, we did introduce pore pressure. The concept of pore. Oh, by the way, there was I uploaded an update of the slides. There was a mistake in example problem number 5. Here, it was, these are wrong. These were wrong, and I fixed it. And actually, the TA told me that it was wrong last year too, and he was trying to tell me, he was actually taking the class, and I misunderstood his question. I thought he was asking me about something else. And that's how I missed it. So this was fixed. Actually, everything else is correct, was correct. But if you plug it in and try to do it, you wouldn't get the answer that I have here now. You will get, but the previous version was wrong. Yeah, it had like 215 minus 250 instead of minus 500, and then it had different numbers. And yeah, I mean, that was arranged such that the normal stresses are the same, but they're not principal. Yeah. Thanks to Justin and Kalu for pointing this out. Okay. We talked about offshore. And then let me use a free slide insert. How about, oh, it doesn't let me. I want to add a new slide. It's okay.
No, you go enable editing first.
Enable editing.
Then you have all the-
Oh, yeah. Thank you,
Go insert or
Mr. Hakim. Where is new slide? Okay. I think that's good. I will just make it to draw. Okay. We did talk about, I'm trying to understand now where we are. So I'm trying to make you understand where we are. So far, I have this rock. Now it's loaded with the principal stresses, right? Oh, yeah, this is the REV that we were talking about in the previous lectures. And they are loaded with principal stresses, in situ stresses, as we call it. Yeah, it doesn't matter the relative magnitude. I just want to show you the concept like, okay, they are loaded, it's loaded. You either have SV, SH max, SH mean, or you may have or S2, S1 maybe, or S3. You know, you can use any kind of nomenclature, but these are stresses, external stresses applied on the REV, right? They are not coming from the REV. On top of that, or from within the REV. But the REV has holes in it. These are pores, and the pores are interconnected. And they are filled with fluid. Yeah, fluid under high pressure. So we have PP, right? And we said that PP acts in every direction. So now we have, let's just say we go with the Andersonian stress regime. We have sigma V, which is basically SV minus PP. We have sigma H max, which is SH max minus PP. We have sigma H mean, which is SH mean minus PP. Or maybe I want to be with the not Andersonian. I want a different system. Yeah. I want to do 1, 2, 3. Then this is 1, 2, 3. What if I'm arbitrary, have X, Y, and Z just arbitrarily? X, X, S, X, X, S, Y, Y, S, Z, Z. Yeah, everything the same. So I want you to be comfortable moving from effective to absolute or concentrated values, as they call it, and the other way around. So be very careful when you see, that's why I was saying in the homework, the word effective is a keyword there. The word, it tells you sigma and not S, etc., etc. This is what I wanted to show. In a nutshell, I mean, here we have basically what I was trying to draw. And you see the whole network is very complicated. Sizes vary, the size distribution varies, but remember that pore pressure acts in every direction. That's why mathematically, if I go back, how do I use that? How do I do that matrix-wise in linear algebra? What I did here with the pink letters.
Yeah, you added the pore pressure to every stress, basically.
Yeah, not every stress.
Resisting to the main stresses.
All the normal stress.
Normal stress.
So I have a matrix S, SP, sorry.
SP.
Sorry, the matrix is sigma.
Principle.
Yeah, but I want to do, well, on the left side, I want to solve for sigma matrix of, basically it should have, it has values like this. I don't care what the value is. It's a 3 by 3, right? And to get this, I have the S matrix, which is, let's say this is the S matrix. It has different values. And I'm gonna write on top of the arrow if you don't, I will erase the arrow. Don't want to confuse anyone. And then I subtract minus PP, but PP is one value. So how do I subtract that from the S matrix?
from the principal stress.
Yeah? How do I do it vectorial? How do I do it matrix wise? How do I do?
Do it in the diagonal stresses.
Okay.
Yeah.
How do I get that PP?
Multiplied by I.
Yeah, what is I?
I is the.
Yeah,
the
that's correct.
diagonal matrix of one.
Yeah. Identity mate. Yeah.
That's what
Yeah, very nice, very nice. Excellent. Excellent. So I have 1, 1, 1, everything else 0. Right? And how do I write that in a simple symbols, let's say? I have
PI.
yeah. Sigma equals to S minus PPI. Yeah. So you understand how vectorial like this is basically all this, which is what we did.
Yeah, it's like to transform a scalar number to.
Yeah. So any questions about that?
What's the function in MATLAB for identity?
DN1.
No. We have zeros, we have ones.
Ones, zeros, IND,
I guess
No.
so.
ID, maybe I? No, it's not I. No idea. I don't remember. It must have a function,
We
yeah.
have ones, we have zeros.
Yeah.
Those are
Yeah. But identity, I don't remember. I, E, Y, I. E, Y, E. And then you say the size next to it in parentheses.
It's like
I, your I,
yeah.
E, Y,
Yes,
E.
yes, I remember it.
And then parentheses.
Yes.
Yeah.
And in parentheses, just the size.
The size, yeah. So basically you write in MATLAB E, I, 3,3.
Yeah, or
And-
only if it's going to just only 3. And
Yeah.
effectively-
Yeah, it should give you this
Yes.
if we do it correctly. Yeah.
Fine.
So, okay, we already went through this slide. And we went through this. And for pressure and overpressure, we went through that too. Are there any questions on that? We are gonna get more on the applied side in the module 4, which is basically wellbore stability and stuff like that. And we did talk about that. Now, last time I told you for roughly 10 MPa per kilometer for the hydrostatic. The correct answer is 9.8, but it's often moved to 10, like for, I guess, one significant figure. So here, when we have 10.12, we are really over pressure compared to here, which we have 9.8. Yeah, we did talk about that. And then we talk about overpressure mechanisms. Yeah, we talked about, we made an exercise, we made a schematic for Louisiana, and then we talked about the effective stresses, and then we were just about to start talking about matrox, and we had to leave. So, as we said, porosity measurements are used to predict overpressure in matrox, like shale, as porosity in clay-rich solids is reduced with effective vertical overburden stress. Now, this is important. Porosity in clay-rich solids is reduced. I will underline is reduced with effective, I will underline the effective too, vertical overburden stress. Now, when you hear clay-rich, clay, think about water. Like whenever you have clay, like clays like water, they absorb water. So we have this equation that you have already seen in the homework, but basically this is like an approximation, and it's used for matrox. I will say for this class, don't use it unless I tell you so. But in shale, in general, what we call shale in petroleum engineering, geology is called matrox. And this is what we are looking into for oil. This is where oil is created, is like the host rock, the source rock. Yeah, and host, if we call it a reservoir.
Place.
Huh?
140 it goes by place, shall play.
Shale play, yeah,
Yeah.
yeah. So yeah, remember the effective stress and not the total stress is what causes mechanical compaction. By the way, what would you think if I give you like a SV value of and a PP value that is bigger, SP value of X and a PP value of bigger than Y bigger than X? So if I tell you, because we said that, okay, let me make it clearer, sorry for bringing too many symbols, but okay, what if SV is 1,000 PSI? Pore pressure is, what if I tell you that is 1,100 PSI?
It doesn't work.
Yeah. What would you tell me? Yeah, what would you tell me?
It's like the pore pressure is lifting the ground.
Yeah, you are lifting the overburden. So is this a logical? So you would say that, no, it's not possible to have sigma V smaller.
Except if you have the ground faulting on the
Maybe we need to ask our chair department, maybe.
No,
In Moon or Mars, they have this.
yeah, you know you're gonna be lifting the overburden, at least not in stable conditions. So you cannot have pore pressure being bigger than any of the in situ stresses. If the smallest one is SH mean, pore pressure needs to be at least,
Same.
yeah,
Of the same
yeah, or
level.
smaller, yeah.
Because, yeah,
The compaction, therefore, is not done by SV, it's done by sigma V. Because you may have a big value for SV, but sigma V may be zero, a little bit over zero, maybe very, very small. So this is an important point that we have here.
depends on the stress regime of the area.
Yeah, of course. Under hydrostatic pore pressure conditions, the SV will increase proportionally with depth. It's what we have seen in the homework. But the log I gave you, remember, is SV, not sigma V, on question 3 of the homework.
And you give the pore pressure.
Yeah, I gave the pore pressure 42 MPa. However, in the presence of overpressure, sigma V may increase less steeply or even decrease with depth. So you may have SV decreasing with depth. And I will show an example if we have time today. Hence, matte rocks exhibiting porosities higher than the porosity expected at that depth for hydrostatic conditions indicate overpressure sediment intervals. Okay. And I will make an attempt to do that today, I hope. And I think you're going to understand it better if you see, once you do the homework, but okay. So we are back to where we were last time.
We'll see.
Norma, Nola.
The
New
beach
Orleans.
house or place
Yeah.
in Louisiana.
This is Berpont Street, where they drink and they, anyway.
The Baton Rouge.
Yeah, no, Baton Rouge is 1 hour this way. Baton Rouge, you have to go this way 1 hour to get there in the fog, in the humidity. These are wild places. And we have the water known as the Gulf of Mexico. And as we said, I hope I do it correctly here for the other plots. I will make it a little bit, I kind of want to make it a little bit deeper. Sorry about that. Let me, okay. And we said with time, sediment layers build up, they get deposited like this, they get deposited like this, they get deposited like this, and they build up, okay? Now they build up, and then slowly, the pore pressure fluids start escaping. But they escape very, very slowly. They escape slower than the sediment builds up. So they create overpressure. They create an overpressure zone. Now, let me put my note. I don't want to make a mistake. I'm sorry. Where is it? If I find it.
The fluid start escaping from the pores because of the sediment deposits.
Yeah.
Yeah, it's like.
Yeah, it's compacted.
Yeah.
It's trying to move up,
Like,
but it's not moving as fast as.
Sedimentation.
Yeah.
Yeah, rate of sedimentation is higher than the rate of yeah,
Of the fluid flow.
exactly. Okay, let me not make a mistake. Okay. What do we have here? Pressure traverse, pressure or stress, depth, TVD, vertical depth. Okay. Maybe I should have done it where the water level starts. Yeah. Yeah, I didn't make it easy on myself because I want to draw another one next to it. Pressure and let me write it here, TVD, okay. So as I go in the water, there is no pore pressure, but there is the hydrostatic weight of the water. Yeah. And then I carry on with the effective vertical stress.
Should be higher, right?
Yeah,
Should be an angle, right?
yeah, I didn't make it.
Yeah, that's good.
Yeah, but I,
You want to.
yeah, I should have made the first one
Narrow.
narrower, yeah.
Yeah, because it has like a high slope.
Yeah, then you
But it's,
become,
It's less gradient.
then you increase the gradient like that. And now you have the pore pressure, which the pore pressure will follow the hydrostatic, right? Up to the water because it has the weight of the sea above it. And it's going something like this, and then this. So let's just call PP, and then we call, is this sigma or S? The sigma. Sigma. The compaction is made by the, yeah. Oh, actually, sorry. No, you are right. Let's just do that to be S. You're right. This is S, the stress.
Because S minus P.
Yeah, and you are gonna have
You
the,
have sigma.
yeah.
Okay.
So the gap between the two lines, what is it?
S sigma.
Yeah.
The air between.
What color shall I make it? Pink?
You're
Okay, sigma V. Are there any questions on that plot? Okay. Now, I will try to plot next to it another plot. Very similar that has phi, porosity, and TVD here, and it's sort of the same axis with that. So up to the mat line, which is the sea floor, we call it the mat line. I will make it orange. What is the porosity up to the?
doesn't exist.
Yeah, it doesn't exist because water doesn't have porosity. And then I have a variation of phi So what color shall I make that? Red?
Yellow most of the time.
Yellow? Okay, I will make it yellow. It goes like this.
It's a fun point.
Yeah. Now, this one,
Story, it's commercial.
it would be sort of like this.
It's like minus goes down.
Yeah, I didn't do it as I wanted. You want it like this, it would be what you expect. The dotted line is what you expect, so sort of it starts like this, then carries on like this. This is with hydrostatic, okay? Now, if I have overpressure here, I will be following this. So this is overpressure, the solid line, and this is hydro. Yeah, that we right. Okay, and then how does that translate in the left plot for PP? Because if PP was hydrostatic, it would be following the slope of the cyan line, right, for the seawater. So this region here shows me overpressure, right? And this region here, same thing. It shows me overpressure, right?
Why hydrostatic pressure is like that? Because you took it as the
0.433.
0.433.
Yeah, the freshwater density.
PPG bucket.
But how does, so what is the effect? Let's explain this, the right side plot, the far right plot. We have here phi equals phi naught e to the minus beta sigma v, okay? And this translates to phi naught e to the minus beta, this exponential, by the way.
So is that to express hydrostatic or the overpressure?
That is to express the overpressure. Okay, and you will see why. Okay, how do I understand it? From an increase in porosity. So I get porosity, I expect it to follow the dotted yellow line, but I get it to follow the solid line, higher than what I expected. And I say it's higher than expected because it's overpressure. So I measure higher porosity, and I say it's because I have higher pore pressure than what I expected. How do I explain it with this equation? It has to do with what happens. What color shall I use here?
So if we are only hydrostatic, what would be the equation?
It will be the same equation.
A P 0.
No, it's gonna be hydrostatic. This one would be 0.433 times the depth.
Okay.
Okay, now it's bigger. So what does that do to what is in the parenthesis? What does that do to what is in the parenthesis? If my pore pressure is bigger than what I expected to be?
Decrease the parameter.
Decreases what is in the parenthesis.
Yeah, it's like okay, now.
And what does that make P?
Increase the volume.
Increase, right? Higher. Yeah.
Sorry. Then,
Yeah.
like,
If I was expecting hydrostatic
yeah,
and I'm getting,
same value.
yeah, okay,
This
I'm getting a bigger pore pressure than what I expected. So this is bigger, this, the pore pressure. This value is bigger than what I expected. So this value,
Needs to be close to SV to have that.
so this value is smaller than what I expected. What is in the
Oh,
parentheses?
yeah. It's
Right?
like the delta,
Yeah. The difference between the two.
Yeah.
Okay. So what does that do to phi? What does that do to phi? Which is what I have here.
Less decrease of.
Going to hydrostatic, so
Yeah.
basically increasing the porosity.
Increasing the porosity relative to what I expect.
It's less decrease of porosity.
Yeah. And I would make another plot if I have the time to explain that. Basically, what I will do is I have, it's gonna be easy plot now, P. And now I have sigma V. But what is sigma V? It says V minus PP, right? Okay. And this is the variation I expect. P equals phi sub O E minus vita sigma V. Okay. Now, what will phi sub O be? What will be phi sub O? Phi sub O. Phi sub O, this one. Phi sub O.
Okay, piece of all, okay. Like gonna be to solve it, you have to go, no, you have to multiply. Minus P sigma V should be 0.
0, yeah. So it's somewhere on the, somewhere up there. Yeah. Y-intercept at sigma V equals 0. What happens as sigma V increases? As sigma V increases, as this quantity increases, I'm moving like this, right? On the plot. So my porosity goes down, but if my pore pressure is higher than what is expected, it won't be going down as fast as the equation provides, or I expect. So it's gonna be like a less decrease. This is what Hakim was saying, basically a smaller decrease. Maybe I should have shown this diagram before I showed the other three.
Yeah, you can show the small decrease if you do the derivative.
Yeah.
Derivative function.
Yeah.
So you can see how much it deteriorates.
So your sigma V becomes smaller because pore pressure increases.
Yes.
Yeah. And because pore pressure increases, your sigma V becomes smaller, your porosity becomes bigger than what you expect. So
that means like if the pore pressure increase, we don't have this. We will have something like this.
less steep, more even. Okay, so if you're reading a porosity log and you get a higher value than what you expect, you will expect a higher than hydrostatic pressure there, let's say, or an overpressure. Yeah, that's the idea about these plots. So now that you are familiar with the pressure traverse diagrams, you can see that how they should look for normal faulting, strike slip faulting, and reverse faulting. Basically, we have SV, SH max, SH min. And for normal faulting, we have the red line on the top plots. So let me, for the online people, I need to get the. So I'm reading from the top two plots. And I'm reading SV is the biggest. Then I have SH max, then SH min, and then PP. I never have PP bigger than any of the three, right?
Yeah.
With overpressure, the blue line moves to the right. So from hydrostatic, it moves to the right. It affects everything else. Yeah.
To the SH min.
Yeah. For strike slip, I have SV in the middle. SH max bigger, SH min smaller, and again, hydrostatic pore pressure is always smaller, but if it's overpressure, it's bigger than hydrostatic, but still smaller than the S3, which is SH min in this case. And for reverse faulting, I have SH max the biggest, SH min second, SV the third, and then pore pressure moves with overpressure, it moves to the right, still smaller. The blue line is always the smallest.
Yeah.
But I think you can understand now these plots. And this is what I expect from traverse plot if I have knowledge of the Andersonian stress regime. And with that, I think the other class is waiting outside, so let's finish it because I'm very afraid of that professor, you know. Anyway, thank you very much. Have a nice rest of your day. I will see you on Wednesday. And I have office hours tomorrow at 1 to 4. If you have any questions, yeah. Or the TA and me are available by email. We are not gonna solve it for you, but I think I walked you through everything. Thank you very much. Have a nice rest of your day.